This is the video for the test review problems for our test on theorems and some first and second derivative stuff, inverse functions. We'll take a look at the list of topics for the test. But what I'd encourage you to do, for you folks who are in my class, is to pause the video right now, take a look at this problem. This is just kind of like a warm-up, and it gives you a chance to practice theorems, and after you do the problem and after you do the write-up, resume the video and see if you got it right. So I'm going to jump in now, so if you're going to pause the video, now would be the time. Reading is the most important thing, so let's read through this problem and see what it tells us. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup from 0 to 6 is given by a differentiable function, so that is an important part of the reading. So we have a function that is differentiable, and the function's name is c, so c is differentiable. Time is measured in minutes, and selected values of c of t are given in the table, and we can see from the table that c of t, the coffee, is measured in ounces. Okay, so why is it helpful that they tell me that c, the function for the amount of coffee in the cup, oh, let's write that down by the way, c of t is amount of coffee in the cup. So it's really helpful that they tell me that the function c is differentiable, because we know that if a function is differentiable, that guarantees continuity. So really, by them telling us that the function c is differentiable, they are also telling us that c is continuous, which means that that is leading us to, whenever you see words like that, you can have a pretty good idea that you're getting ready to encounter a theorem, because we have some conditions that are met. All right, let's go back to read and see what they want us to do. All right, so we have our values in the table. We have minutes right here from 0 to 6 minutes, and we have the number of ounces of coffee in the cup. So the question is this, or in the coffee, filling a large cup, cup. Is there a time? This is another big giveaway that we're probably encountering a theorem. You'll see this very often. Is there a time makes me alert to this is probably going to be an ask about a theorem on the interval from 2 to 4. So we're focusing on the interval from 2 to 4 at which the derivative, so the ask over here on the right hand side, c prime, the derivative, first derivative I should say, so c prime of t equals to 2. Okay, so let me go back and analyze my situation. When I look at this, my thinking is that I'm either going to be dealing with IVT or MVT. Now IVT talks about a y value between two other y values on a given function. So the IVT would be saying that you can find the y value of 2 between the endpoint y values of the derivative. So all of this, if it was IVT, everything would be about c prime of t. But when I come back over here and I look at my table of information, I have the original function. So we know that the original function is c of t, and the first derivative is c prime of t. So that leads me to believe that we are dealing with the mean value theorem, because the only information that I have, I can look at the conditions of the original function. To apply the IVT, I would need to know the conditions of the first derivative. And I don't know the endpoint values of the first derivative. So This is basically asking me, is the instant rate of change, this is what the mean value theorem says, equal to the average rate of change? So I'm going to calculate the average rate of change. So I'm going to need to pay attention to the x and y coordinate for the first endpoint and the x and y coordinate for the second endpoint. So in my work, I'm going to calculate the average rate of change. So I'm calculating original function, c of 4 minus c of 2 over 4 minus 2, and the average rate of change that I calculate is an average rate of 2, which works out beautifully. Because since the average rate of change is 2, then because the conditions are met, because remember, come back up here to the top, they told us that c is a differentiable function, which means that c is a continuous function. So the conditions of the mean value theorem are met. C is continuous on the closed interval and differentiable on the open interval. So since the conditions are met, the promise will hold true. So here's my write-up. I'm going to declare condition 1 and 2. Since C of t is differentiable on the closed interval for 2 to 4, that's what leads me to, and this order matters. They told me that the function c is differentiable. It's my conclusion that c is continuous. So the order that you write that in matters on the closed interval. And you could write, yes, that's right. The average rate of change on 2 to 4 is 2, and I have to show that calculation, which I did above. Therefore, there must be a time t on the interval from 2 to 4 where c prime of t is equal to 2. You do not have to declare the mean value theorem. You also, so I'm going to cross it out just because you don't have to say it, but you can say it. They do not ask me to figure out the time when this happens. They just said, is there a time? And I can guarantee you by the mean value theorem, there will be a time. So I hope you did well on that. All right, let's see what College Board does. That was a real AP problem, by the way. So just like I said, in part B, which this was part B of this question, the common error presented was an appeal to the intermediate value theorem. So that was the mistake the students made, and this is what College Board tells us. They did a write-up to share with students and teachers. Based on your experience, what would you like to send to teachers to help them help their students? It's very important for students to have a solid math background before taking calculus. Students frequently make arithmetic and algebraic errors while attempting to do calculus. I'm not sure why that was helpful, but that's what they said. Okay, so now to your packet, page number 42. As you know in my class, if it's on the review sheet, if the topic is listed, it is on the test. Not going to read these two, but let me see if there's anything that I would highlight. Clearly, make sure you're able to write. That's what an example of what I've just gave you. But you can read these topics and you can go through your packet and make sure that you are ready for the test. I'm going to jump into the problems. So for this video, I'm only going to look at problems 1 through 4 because that was the first assignment. And I have the solutions posted. If you don't need the video and you just need the solutions, they are there. But I'm going to walk you through my solutions. So in problem number 1, for each of the following, find any values C in the given interval at which the mean value theorem applies. Sketch the graph of the function and then sketch the secant and tangent lines. That's just a visual representation showing the lines are parallel. Justify your answers with complete sentences. You may use your calculator to help you with the graph of the original function. So if I were going to make you do some sketching of secant and tangent lines, I would provide the graph on your test versus having you sketch the graph. You would just be doing the secant and tangent lines. Here we go. For letter A, we have the graph of 6 over x, which is a rational function. We have the closed interval from 1 to 4. I know that there is a discontinuity at x equal to 0. So the function is not continuous at x equals 0. However, the good news is 0 is not on the given closed interval. Therefore, this function is continuous on the closed interval and differentiable on the open interval. Therefore, the mean value theorem will apply. So remember, you have to substitute the x values into the original function to get the corresponding y values. So that's where I got 6, and that's where I got 3 over 2. I have to calculate the average rate of change, so change in y over change in x, and set that equal to the instant rate of change. So this is my average rate of change. This is my instant rate of change derivative. I have to do the arithmetic work very carefully and slowly, and when I do that, I get negative 9 over 2 over 3, multiplied by the reciprocal, so that cleans up to negative 3 over 2. I'm going to cross multiply right here, and I get negative 3x squared is equal to negative 12, and you follow the algebra. Now I do get a plus or minus 2, however the interval, remember, is from 1 to 4, and negative 2 is not on that interval. So even though the derivative is equal to negative 3 halves at that value of x, I'm not going to report it since it's not on the closed interval. So here's my write-up, and the write-up is going to be important for your test. So my write-up is here. Since g, be specific, not the function, since g, original, is continuous, be specific, closed interval, 1 to 4, has a derivative on open interval, 1 to 4. There is a value of x where the average rate of change is equal to the instant rate of change by the mean value theorem, and that x value is 2. Then you can see down here that I created the graph. I only needed the right-hand side of 6 over x, so this is the graph of 6 over x. I drew the secant line in green right here, and then the tangent line is going to be parallel to that. And if you look at that right here, if you go up from 2, you can see that the purple tangent line is tangent at x equal to 2. All right, moving on to 1b. So h of x, let me clear these annotations out of the way. In 1b, I have a square root function that has been vertically shifted up 5 units and reflected. So again, I said you could use the calculator to support you on that. Let me make this bigger, fit to width. Okay, so I know that I can't, so I have a square root, and I know I cannot take the square root of a negative number, but 4 to 9, I don't have any negative numbers there, so that's a good thing. So I can declare square root function. The parent function, remember, looks like this, and that is a continuous function over its domain, and it has a derivative over its domain. So the conditions are met. I have to calculate the y values myself by substituting 4 into the original function, so I'd have to find h of 4 and find h of 9. That is how you calculate the y values for the endpoints. Here I am finding the average rate of change, change in y over change in x. Over here is the instant rate of change, which is the derivative of the given function. When I do the calculations, I get an average rate of change of negative 1/5. And when I apply the power rule, well, I've already done the power rule, got the derivative, but I'm going to do a rewrite algebraically, and I'm going to move that x to the negative 1/2 power to the denominator and change it back into a radical. To solve this equation, I'm going to cross multiply. So negative 5 times negative 1 is positive 5, equal to square root of x, divide by 2, square both sides. So we don't get a plus or minus because we're squaring. Plus or minus is when you square root. We get 25 over 4, and 25 over 4, we had the closed interval was 4 to 9, and 25 over 4 is 6 and change, which is between 4 and 9. So I'm going to do my write-up again. Since the given function h of x is continuous on the closed interval and differentiable on the open interval, there is a value of x where the average rate of change is equal to the instant rate of change, and the value is 25 over 4. Number 2. Now we're moving on to Rolle's theorem. State the hypothesis of Rolle's theorem, which are not met on the given interval. So this problem's already telling you, not going to apply. You just got to figure out why. Remember, for Rolle's theorem, there are 3 conditions. We have to have a function that is continuous on the closed interval. We have to have a function that is differentiable, has a derivative on the open interval, And thirdly, we have to have the y value of the endpoints have to equal each other. So basically what this problem is telling you to do is to figure out which of the conditions is not met. So for letter A, we have a quadratic, which is going to graph to be a parabola. So we all know that parabolas are continuous everywhere. We know that parabolas have a derivative everywhere. So criteria 1 and criteria 2 are met. It has to be that the endpoints do not have the same y value. So I'm going to substitute 0 into the function. I'm going to substitute 1 into the function and show that f of 0 does not equal to 1. Therefore, Rolle's theorem does not apply. So the derivative somewhere could be 0, but I can't promise it by Rolle's theorem. So here's my write-up. F of 0 does not equal f of 1. Rolle's theorem does not apply. I don't know why I kept writing. Rolle's theorem does not apply on 0 to 4 because Rolle's theorem does apply. Oh, I forgot there was a second part to this question. Yes, sorry. So then it says, then give an interval for each function where Rolle's theorem does apply. Okay, yeah. So there's two things I'm doing. I'm telling why Rolle's theorem currently does not apply on the given interval, and then I want you to give me an interval where Rolle's theorem does apply. So since for this one we broke the condition number 3 that the endpoints don't have the same y value, then I have to figure out an interval. I have to figure out two x values that do generate the same y value. And so if you go from 0 to 4, if you change your interval from 0 to 4, when x is 0, y is 0. When x is 4, y is 4. So Rolle's theorem does apply on the closed interval from 0 to 4. So in other words, I'm just fixing the condition that was broken originally. All right, let's clear that and go to number 2, clear the annotations. In number 2, I have an absolute value function, and we know this absolute value function is shifted to the right 2 and down 1. So to the right 2, 1, 2, and down 1. We obviously see that V shape happening, so there's a sharp turn here, so there's no derivative. And the interval is from 1 to 4. So I can already see the condition. The problem here is that the function is not differentiable on the open interval. So the function is continuous on the closed interval, as you can see here. The function is not differentiable on the open interval, so the theorem does not apply. Since g of x is not differentiable at x equal to 2, Rolle's theorem does not apply. Then it said, well, then fix the condition. Well, we can't. We can't apply this anywhere. Rolle's theorem does not apply to any closed interval because the only way to make f of a equal to f of b is to include this point where there's no derivative. In other words, we'd have to use symmetry to get the same y values. So we cannot make Rolle's theorem apply on any interval of this function. Number 3, decide if the EVT, now EVT is easy because EVT has one condition, continuous on the closed interval, and if the theorem applies, we're going to find the absolute maximum and the absolute minimum, the highest y value and the lowest y value, write sentences. Okay, my work for number 3. So I'm coming back to a quadratic equation which is continuous everywhere. Therefore, it's certainly continuous on the closed interval. So to apply the EVT, I have to find the candidates, which are endpoints and critical numbers. I find the first derivative, and I set the first derivative equal to 0, and I find a critical number of 2. The first endpoint's -3, the second endpoint is 3, the critical number is 2. Now, the important thing here is to substitute into the original function because you're trying to compare the y values. And this way you might use your calculator to calculate that on the test. Since I'm not letting you use a calculator, I would give you reasonable values. And we can see that the highest y value occurs at x equal to -3, so this is the absolute max. 51 is the absolute max, and the absolute min is 1 and occurs at 2. Check out my write-up over here. Make sure your math eyes read very carefully to compare your write-up to my write-up and make sure you're on the right track. In 3b, we have a cubic function. A cubic function is continuous everywhere, therefore it's continuous on the closed interval, so we're good to go. So in 3, same process. I'm not going to keep going too deep into this. First derivative, set equal to 0, so we do have to be able to factor. We have two critical numbers right here. I'm going to create my table of values. I have the endpoint, I have the other endpoint, I have a critical number and a critical number. They go into the original function. So it'd probably be a good idea to use a calculator on this one. Check out my write-up and make sure you understand that and that you wrote correctly. And then the third function, we have danger, danger. We can't let the denominator be 0, so I'm going to set x squared minus 1 equal to 0. And I get x equal to plus or minus 1 where there are going to be discontinuities. Now, the condition of the extreme value theorem is that I must be continuous on the closed interval, meaning I have to be continuous at 1 and I have to be continuous at 3. I'm not continuous at x equal to 1 based on my work that I just did right here. Therefore, the extreme value theorem does not apply. And that's what I wrote up here. Since the given function, and I should have named it, but maybe it's just called y. Since the given function is not continuous at x equal to 1, which is on the closed interval, the extreme value theorem does not apply. Question number 4. Let's clear these annotations. And this is the last question of the first part. If the second derivative, so they're giving me a second derivative function, is equal to 2 ln of x squared minus 1, the first derivative at 4 is 0. So your math eyes should be going, oh, that's a critical number. This is the second derivative. Let's see what they're going to ask us. Tell whether a local max or a local min occurs on the original function, g of x, at x equal to 4. So hopefully you are realizing that this is the second derivative test, which says you can use the second derivative in many cases to find a critical number. You have to know your number 1, you have to know the critical numbers, and we do. Number 2, you're going to substitute your critical numbers into the second derivative, and you are looking for the output, the sign of the output. If the second derivative is positive, you have found a local or relative minimum. If the second derivative is negative, you have found a local or relative maximum. So I substitute 4, my critical number, into the second derivative. There's me substituting 4. 4 squared is 16 minus 1 is 15. The ln of 15 is a positive number, times 2 is a positive number. So if I have a critical number substituted into the second derivative and the output is positive, a local minimum occurs at x equal to 4, look at the write-up, and is g of 4, look at the write-up, because the first derivative is 0, that's the establishment of the critical number, and the second derivative is greater than 0. And this, that I just put in parentheses, is the second derivative test. You don't have to declare that. I just want to make sure that you know it. All right, so that's 1 through 4. I'll do another video for the rest of the review and for the extra test prep.